Olomola.
Please listen to the biography of Professor Temitope Olomola. Professor Temitope Olomola joined the services of Chemistry Department of Bafemi Awolowo University, Ile-Ife in 2006 and rose to the rank of professor in 2021. He has served in different capacities in the university, such as chemistry coordinator for the pre-degree program, elected member of the University Senate, and elected member of the University Appointment and Promotion Committee. He is currently a member of the Postgraduate Board, the editor-in-chief of Physical Sciences of the Ile-Ife Journal of Science, and is sectional editor of Chemical Sciences of the Annals of Science and Technology, which is the official journal of the Nigerian Youth Academy. Professor Olomola's research thrusts involves using basic synthetic chemistry tools to find solutions to the poor man's diseases which are particularly endemic to Africa, such as HIV-1, sickle cell anemia, and malaria. Specifically, his research combines the synthesis and evaluation of heterocyclic compounds with medicinal potential, asymmetric synthesis of drug-like molecules, and kinetic mechanistic studies of organic reaction mechanisms. Professor Olomola has been involved in the development of science through various community engagement initiatives. Efforts in this direction led him to receiving the 2011 Rhodes University Engaged Students of the Year Award and the Investec Rhodes Topic 100 Award, Community Engagement 2011. While at Rhodes University, he was the chairman of the committee that organized the first regional postgraduate conference in the Eastern Cape of South Africa. Professor Olomola became a member of the Nigerian New York Academy in 2015 and served as the fourth president of the Academy between 2017 to 2019. He was also a visiting researcher at the University of South Africa from 2018 to 2020 and the University of Southampton between 2014 and 2015. He's a fellow of the Nigerian Young Academy, the African Science Leadership Program, and the Ife Institute of Advanced Studies. He was a member of the planning committee of the 7th World Conference of Research Integrity hosted in Cape Town, South Africa in 2022. He was one also of the facilitators of the Nigerian Science Leadership Program. Ladies and gentlemen, please with a warm round of applause, welcome Professor Temitope Olomola to the microphone.
Okay. The Vice Chancellor in absentia, Deputy Vice Chancellor, the Dean of the Faculty of Science, HODs here present, keynote speaker, who is also a distinguished comrade. Ladies and gentlemen, I'd like to, while we fix the technical issues, my presentation this afternoon now is simply going to be about trying to showcase what chemistry can do in the area of medical sciences. So, the topic before me is chemical innovations in drug development, from research to patient care. Like I said, the background is against chemistry. I'm a synthetic organic chemist, and so I apply my knowledge of chemistry in the area of drug design. So, by way of introduction, the discovery and development of new drugs have revolutionized healthcare, transforming once fatal diseases into manageable conditions. So in simple terms, we now are able to apply drugs to making life better for ourselves. Now, but central to this whole process of drug development is the basic knowledge of chemistry itself. And so our conversation very briefly this afternoon will be around understanding the role that chemistry has to play in the area of drug discovery. But drug discovery is not, I know if you go to the pharmacy shop, you see quite a number of drugs. So at times, you may not appreciate the process it takes to get or to make a single drug. If I ask you how long do you think it will take to make any drug, maybe Fancida or how long do you think it takes to make a drug, roughly? You may ponder on it. I don't want to, since it's not really a workshop per se, but it's a long, expensive, and complex process. Okay, I'll show in one of the slides to follow a rough idea of how long it takes. So, at the core of the process of drug design is a clear understanding and application of chemistry, targeted towards molecules that are able to help alleviate a particular kind of pain. The basic history of drug development. So, how did it all start? Well, like we know from the name tree is the one we call dogoyaro. Okay, that's dogoyaro is not from this side of the country. Dogoyaro is actually the name from the northern part of the country. So that tree at some point was found to help with the treatment of malaria, okay? And so at the early stage, efforts were getting chemical principles out of plants, okay? And so we had a lot of herbal drugs, and if you have seen researchers who do phytochemistry, they basically try to get active components from plants. All right, and as well as serendipity. So without really knowing, we stumble on something. If you have read some of the history of some of the drugs or general, for instance, antibiotics, there was some component of serendipity in there. But yeah, so if we go through across the different eras, you saw that drug development has traveled quite a distance. But perhaps to mention the fact that, sorry, when we began to do combinatorial work, combinatorial chemistry, it was a significant landmark, as well as, of course, the emergence of computers. Okay. Now, what then is the role of chemistry in drug discovery? Like I said, my talk is actually trying to help us see where chemists come in looking at the whole concept of from patient or from research to patient care, how we come in that cycle. First, fundamental research. Chemistry is a pivotal role, okay, in basic research. And when we say basic research, we're saying we synthesize an array of compounds. We so separate them, okay, either those compounds or compounds from nature, we isolate them, okay, and then we go ahead to carry out in vivo and in vitro analysis. That process that I have just described is not in fact, it could take the lifetime of more than one project student, even at a postgraduate level, to complete something that simple. Okay? To design or synthesize a few compounds and just do basic vitro in vivo analysis. Alright, so that role is peculiar. Chemists are involved at that stage. But I'd like to show just, and I promise this is the only complicated, in quote, slide because of the structures. Okay, the next three slides explain or describe this. Typically, what we do as organic chemists is to get a particular molecule, we call it a target molecule, and then in a few steps, using our knowledge of synthetic organic chemistry, we try to look at how we can build up this molecule. Okay? I will come to how we get to this target later, but essentially we try to look at how we can build up the molecule. And so by just breaking some basic bonds around that ring there, we can come to these two precursors, which if we add together, will give us the porous compound. And then we can also break down one of those further. And so essentially what we do is we keep breaking them down till we get a form that we can buy commercially. Okay? So from what we can buy commercially, we can then build up such a, well, not so big, but, well, relatively simple molecule. Okay? And I'm sure if you look at the, the paper they normally put in the medications that you buy, if you open some of those papers, you will see the structure of some of the compounds, the active ingredient in there. So you see things that look of this type. So what we will do if I were to put a maybe master student on this project, for instance, is he will spend a few months, taking that reaction. We call it simple benzyl protection. He does that, and then he reacts with that in a simple step to form this. Now, all of this simple arrows I'm drawing, okay, the candidate would need to take some time to make the compound, first be sure the reaction has worked, and then also go ahead to confirm that the structure is what we are saying it is, or what we expect it to be. So it involves a lab work, some instrumentation as well, and some data analysis. Okay? But the basic summary is that we come up with being able to synthesize that molecule that I had on the previous slide. And in fact, that compound we synthesized a few years back is a compound that is supposed to have what we call a dual inhibition role, able to, on the one hand, inhibit one part of HIV-1 integrase, and the other side able to inhibit HIV-1 reverse transcriptase, okay, which are two critical enzymes in the life cycle of HIV-1. Okay, so that is basic research, and the last part of the basic research is we'll go ahead to then check what the kind of response we see when we test these compounds with the live cells. Okay, what it looks like. Okay, I'm trying as much as possible, being conscious of our audience, to explain what we're trying to do. All right, so, but at the end of the day, we see that, the compound has some level of activity. Now, in research, this compound that we have more or less stumbled upon by starting from a series, would hopefully look at them as, we call them HITs, H-I-T. Okay, a HIT compound is a compound that we realize is showing activity at the end of this first basic research approach. Okay, so we identify HIT compounds. All right, so going back to the role of chemistry in drug design. The next critical thing is target identification. So every disease is caused by something. There is a parasite responsible for malaria. There is a virus responsible for so on and so forth. All those diseases are viral. So we try to understand the target. Okay? So we identify the biomolecule that is involved in the life cycle of that particular disease we're talking about. And then we can, using high throughput screening methods, begin to understand the nature of that target. Once the target is understood, like I said earlier, we use our understanding of the target, okay, to then identify a hit. Okay, so the summary is that we, with basic tests in the lab, say that, this particular compound is showing good response. That is, it is inhibiting, if it's an enzyme, inhibiting the functioning of that enzyme. Okay, so by identifying that, now remember the target itself is, a bigger molecule. It could be an enzyme, a protein, generally a receptor of sorts. So we can use our understanding of chemistry to, investigate that surface or that pocket of a receptor. And then the third area where chemists really get involved is in what we call the hit to lead optimization. So, like I said, the first, we identify the compound that is showing some level of response. We call it a hit compound. And then we go on to, in most cases, the hit compound, for instance, may not be soluble. Okay, it's active, but you cannot get it into the body system. It's only maybe water soluble, will not dissolve or enter into a fat-based system. Okay, so we then have to, through a series of careful steps, try to understand how to move that compound from just being a heat to promote all of the chemical properties of interest such that it becomes a lead. Okay? So a lead compound is the kind of compound we're interested in that we actually move into the stage of drug development. Now, so you have your heat. The challenge is that when we generate those heats and we evaluate them, at times some of them fail, and so the process stops there. Okay? Even after you have identified the heat, while you are validating the heat, unfortunately, some of them also fail and the process stops. So what I mean is that we can start with, once we have identified a heat compound, we have ways of doing that. We generate its derivatives, compounds that are similar to it, and then we try them. But unfortunately, some of them will fail. Okay? And when they fail, we just put that aside. We continue with only the one that passes. So for a compound to go all through, it must go through each of these stages to the point of saying that it has actually been optimized as a lead compound. Now, it is only lead optimized compounds that actually are considered as potential drug candidates. And so, on the next slide, you will see that all of what we do in basic research, okay, which takes a lot of time. In fact, you could go to the point of having so many compounds, more than 5,000 compounds, and in some cases, none will make it through the process. So when I say it takes time to make a drug, now that is the angle we are coming from. It takes a lot of time to actually be able to get a compound that makes it through the entire process. It is after it has gone through, okay, as, you know, a lead compound, it comes out, we say, okay, we're on a drug discovery path, then it enters what we call preclinical trials. Okay? And at that stage, we start looking at the kind of effect it has on, not man now, but animals that are considered, you know, to have a similar system by which we can infer. So if you test it on mice or on rats and it kills all of them, you know that it must not, that one has failed, right? So even though it has made it through all of the previous stages, if it gets to that stage and it's, you know, causing trouble, then we know that is out. Okay? Professor Nia is a toxicologist, so I'm sure he too can give us some understanding. So basically, the compound must go through all of these phases to be able to actually get to what we call a drug that is approved to be on the market. The slide below, sorry, still on that same slide, the image below now basically tries to help us summarize that if you start with 10,000 molecules, in many cases you end up with one approved drug. Now, so that is to give you an idea of how expensive the process actually is. And then look at the length of time there. It says 12 to 14 years. Now, there are compounds that you know that you take today. I can tell you that took more than 14 years to actually make it out. Okay? But obviously, when there is a breakthrough and you now have a drug, it then is not so difficult to make other, you know, if there's chloroquine, you can make camoquine and you can make, you understand? So that's not, what I'm saying is to get the one drug that first of all is able to attack the disease in question. All right, so, and the process, as you can see, would vary depending on where the research is being done, but approximately $2 billion US dollars will be involved in that entire process. So it's from preclinical drug development to clinical drug development, where you have phase 1, 2, and 3 trials, and then to market drugs, which is now being described as phase 4, actually, after that process. Because it can go through everything, and then you realize that when people take it, it has a different effect. We have tested on animals, it is fine. We have tested in the lab, it is fine. But when humans take it, and that's why you see that in those slips in the drugs, they write things like the kind of side effects you should expect. Anything beyond those side effects means there's a problem. Okay? So they keep monitoring drugs even way after it has been released, after it is now on the market. You still have to keep monitoring. Because, like the guy said earlier, okay, everything is chemistry. Okay? As I'm talking, there's a flow of ions. And you can hear me audibly because as I speak, chemistry is involved. So if the particular body system is somehow not responding well to the chemical variant that has been introduced, it may work for others, but the reason why some people don't use the same drug for malaria as other people is because it doesn't work for them. Okay? So what works for one person may not work for another person. And so what will give a reaction in person A may actually be fine in person B. All right, so let's go on to modern innovations in drug development because of our time. Now, the modern era, of course, we have so many innovations today. And we know that with time, we have actually advanced significantly. So one of the things that is an area of innovation is the fact that we can today have what we call targeted drug design. Okay, and what we mean by this is that it is actually possible to move away from broad spectrum drugs. If you followed the presentation of Professor Nia very well, he actually alluded to this, that it is possible to have more targeted types of treatment, okay, that is literally specific. It may not be just person specific, it may be specific to a class of people, all right? For instance, paracetamol works well for some, but some people need to use aspirin. Okay, I don't know if you ever looked at the history of aspirin and why aspirin was formed, but I won't go there now. So this basically is because today we can do what we call structure-based drug design or fragment-based drug design. Okay, and by this techniques, we are able to actually go specific with particular biological targets, which in short means we are able to minimize the off-target effects and improve the drug efficiency. Okay, so the first one is targeted drug design. The next one perhaps is a word we are more conversant with, nanotechnology, also applied in drug delivery. So it is possible to use what we call nano-sized drug carriers, okay, such as liposomes, and use them in such a way that first they protect the drug before it gets to the site where it is needed. Okay? In fact, today we administer some compounds. Some of the drugs you even buy now, you are buying a form of the drug. It is when it gets inside you that it metabolizes into the form that actually works. Okay? We call them prodrugs. So you have cases where we can also embed the drug within some kind of capsulate form that allows the drug to transmit and get to the site of action before it actually delivers. So this is all about precision targeting for drug therapy. The next is chemical biology and bioconjugation, which simply is about biologics, such as antibodies, and these have been used